it is very crucial to understand evaporative cooling, especially for high head flux application, such as the servers cooling in data centers. And it has been even getting more important as we use more computing powers in our everyday life. So it is with special excitement that I'm pleased to welcome one of my colleague and friend, Dr. Damena Agonafer, to this meeting. His research integrates thermal fluid science, electrokinetics, interfacial transport, and renewable energy by taking evaporation-based approach to solve those important problems in the world. And his work has been very well recognized by actually multiple awards. So if I name only a few, it includes the NSF Career Award and ASME Early Career Award and Sloan Award, and etc. So you can see the full list of his awards from his bio. And also he has been very active to advise diverse undergraduates as a faculty advisor at his institution. He has PhD degree in ME from UIUC and worked as a postdoc at Stanford Group with me. And currently he's an assistant professor in ME, the Mechanical Engineering and Material Science Department at Washington University, St. Louis. So please join me in welcoming Dr. Damena Agonafer.
Well, thank you very much, Yunjen. And as Yunjen mentioned, part of the reason why I was very happy for her to introduce me is because we did work extensively together as a postdoc in Professor Ken Goodson's lab on a DARPA high school project, and I'll talk briefly about that today. So yeah, I just want to thank you for inviting me today, and we are doing several things in our lab, but today I'm going to focus on evaporative cooling for high heat flux applications. So here's an outline of my talk today. I'll first begin by discussing some of the motivation and look at some of the thermal challenges for high-powered micro and power electronic systems, and then how the role of nano-engineered surfaces materials play on phase change heat transfer. Specifically, I'll be looking at how we can, sort of engineer surfaces specifically for low surface tension liquids, such as dielectric refrigerants. Finally, we'll look at some of the contact line dynamics of hemispherical based droplets and also asymmetric droplets. And then I'll briefly go over evaporation from single microdroplets and evaporation from an array of microdroplets. Finally, I'll conclude with some of the applications that we are currently pursuing in terms of developing an evaporative cooling module for both wide band gap and heterogeneous integrated chips. So I just wanted to kind of give a brief motivation of our work. And I think starting off with data centers, especially during the COVID pandemic is useful. So, there has been an increased demand for data centers for different applications, such as deep learning, online education, and consumer-based services. And, data centers consume approximately 2% of the global electricity, and nearly half of this power is spent on data center cooling. And more specifically, chillers can consume about 33% of this data center energy. So therefore, we have a big motivation on minimizing the thermal resistance for the cooling system. And therefore we could potentially remove the necessity for chillers and, for example, offer some exergy potential or waste heat for buildings. And that's exactly what we see on the lower left-hand corner. We see the significant resistances, for example, associated with air cooling. And if we use different types of cooling methods, such as single-phase cooling or two-phase cooling, we can significantly reduce those thermal resistances For example, especially if we add, for example, immersion cooling, we can get rid of some of those resistances associated with the TEM materials. And therefore, we can use this, again, as some type of exergy potential, such as waste heat for buildings. And so really the motivation here is that as we integrate, higher performance semiconductor devices in data centers, such as, application specific ICs, GPUs, CPUs, the thermal management becomes more challenging. And so I just kind of wanted to give a brief example, for example, of the Google Tensor Processor Unit that is found in their hyperscale data centers, right? And so if we look at the trends here, the power of these TPUs have significantly increased over the last decade. And so therefore, the increase in computing power, as we see, right, is leading to greater heat dissipation. So initially, in the first 2 generations, we can see that Google actually, use air-cooled heat sinks, right, to dissipate the power from these TPU units. But as they move to the 3rd generation, air cooling could no longer dissipate these devices, and so therefore, their data centers were retrofitted, are being retrofitted with liquid cooling heat sinks. And so then the question is, what is driving these higher heat densities, and how can we address these cooling challenges? So this is just, I'm sure many of you know this. This is just definitely probably very redundant for many of you, but if we look at the transistor power, you essentially have 3 different components. You have your dynamic switching power, which in the past was the dominant power. You have your short circuit power and your leakage power. So in the past, if we look at Dennard scaling, we could essentially scale down the transistor size without increasing the power density. So what happened? So if we could look at the current challenge, when we decrease the transistor size, that requires a decrease in threshold voltage, which increases the leakage current. And so therefore, power density is no longer constant. And this is why we've kind of been stuck at a clock frequency around 3.4 to 4 gigahertz. And if we look on the plot on the right-hand side, we can see, for example, at 180 nanometer technology node, our leakage power consumption was significantly smaller, or smaller fraction of the total power. And if we look at 65 nanometer technology node, it was almost nearly half, right, of the total power of the transistor. And so here's actually another, this slide right here is courtesy of Ravi Mahajan from Intel Fellow. He's an Intel Fellow, and this shows a power map over the next several years. And we see here that the main point here is that thermal technologies, right, must be designed not just sort of for the power, but for the average for the hotspots. And they must be, typically 2 to 4 times, right? We need to develop thermal technologies that that can dissipate these hotspots that are typically 2 to 4 times larger than the average power density. And so therefore, if you look at our trend, by 2023, we're looking at, up to 900 or close to 1 kilowatt per square centimeter. So there's a huge motivation to come up with very aggressive cooling strategies in the next several years. So how can we then leverage the current technology node, right? And so one of the things we can do is we can look at heterogeneous integrated chips. 3D stack chips, for example, offer a significantly smaller footprint, a smaller signal delay. You can mix functionality. For example, you can have RAM, you can have processors, right? And also you can mix technology nodes. So for example, on the right-hand side, we can see that typically a 90 nanometer technology node and a 2D package can performs the same as a 180 nanometer technology node and a 3D stack chip. And the same, for example, as a 45 nanometer technology node. Similarly performs like a 90 nanometer technology node for 3D stack chip. And so then the question is, what are some of the thermal challenges of these heterogeneous integrated chips? So if we look at a traditional 2D package, we have, our, TEM1, we have our TEM2, we have our typical sort of package, we have a heat sink on top. And then when we look at these 3D stack chips, they offer smaller footprint, but also they have higher heat density. And the higher heat density comes from heat being compounded from one stack die to the next. And so then the question is, how can we cool these technologies? Well, one way of cooling these technologies is through embedded cooling, which allows for each stack layer to be cool. You can also remove the requirements for thermal interface material, which can account for potentially up to 30% of the thermal budget. And so then the question is, how can we nano-engineer surfaces for enhancing thermal transport processes for dielectric liquids? In addition to some of the thermal challenges for microelectronics, there's also very big thermal challenges for the next generation high power electronics. So, we said that, in the next several years, the microelectronic system is going to, we're looking at 1 kilowatt per square centimeter. But if you look at some of your wide bandgap semiconductor devices, such as your high power inverter systems found in hybrid electric vehicles and high energy weapon systems, we're talking about, tens of kilowatt per square centimeter for these different types of devices. And so, really the conclusion here is the next generation electronics will certainly generate heat fluxes exceeding 1 kilowatt per square centimeter. So therefore, we really do need some very aggressive cooling strategies. Okay, so I just wanted to kind of provide a little bit of overview of what I first started doing as a postdoc in Professor 𝗘𝗃𝗽𝗏𝗁's lab. We were working on a DARPA project, and this is actually where I extensively collaborated with Yunjin, and we were developing a two-phase evaporative cooling module. And we use a combination of copper inverse opal structures, right, as a liquid delivery layer. And we also use what we call we also integrated this with the bilayer, right? And the applications were for cooling wide bandgap semiconductor devices. And we actually, this was a very extensive collaborative effort. We were able to sort of demonstrate that we're able to dissipate heats 1.3 kilowatts per square centimeter. And the idea is that we use a combination of diamond microchannels, and we were able to grow these sort of conformal inverse copper opal structures on these diamond microchannels. And so heat was spread on these channels, and then we sort of liquid wicked through these conductive porous copper structures, actually, that Yunjin is now working on. And the idea is that we use a hydrophobic membrane in order to extract the vapor and retain the liquid inside. And again, the major key here is that we use water as the working fluid. So then the question is, how can we potentially design a system for dielectric liquids? And here is just another image that shows the conformal CIO coatings on these diamond friends. And this was actually published in Advanced Functional Material in 2017. Okay, so then the question is, how can we develop a bilayer or some type of evaporative cooling module for low surface tension liquids? So, I started looking at, non-wetting surfaces, such as, for example, the spring tail, which has these sort of sharp edge sort of reentrant structures. And what we'll see in the next several slides, these sharp edge features essentially allow you to change the interfacial area and therefore changing the interfacial energy. And so from this, we sort of design these hollow micropillar structures in order to stabilize low surface tension microdroplets. And the way this works is really called, this really comes from the Gibbs effect, or it's also called the 𝗘𝗃𝗽𝗏𝗁 effect. And the idea is that as liquid advances, along a solid edge, right, there's a change in this interfacial energy along the contact line. And so what we actually did was we actually performed the free energy analysis of these of how the liquid, right, advances in these hollow micropillar structures. And so first, what we see here is that the liquid initially wicks inside the hole, and then essentially transitions from a concave to a convex, or pivots from a concave to convex menisci. And then this little pressure drop that you see here is essentially the liquid, right, as a cap sphere on the top surface of the hollow micropillar structure that then advances, and then you get this pressure drop. And then finally, the liquid is then retained on the outer edge of the micropillar structure. And that's why you get this sort of pressure increase or pressure barrier. And finally, bursting occurs, or spilling. And so therefore, some of the behaviors are quite different for high surface tension liquids and low surface tension liquids. So for example, for high surface tension liquids, the minimum radius of curvature or maximum Laplace pressure actually occurs in the inner diameter of the hollow micropillar structure. And also, this maximum pressure on the outside does not correspond to the bursting pressure. So actually the maximum Laplace pressure actually is in the inner diameter, as opposed to low surface tension liquids, right? The bursting pressure does correspond to the maximum pressure, and also the maximum pressure occurs on the outer diameter of the hollow micropillar structure. And this is attributed to, and we'll see this a little bit later, but this is really attributed to low surface tension liquids really have infinitesimal contact angles compared to, for example, high surface tension liquids such as water. And so this behavior, this is the reason why you get this sort of different behavior in terms of the contact line dynamics. So we also wanted to look at the validity of our free energy analysis, and we see that at very high capillary numbers, right, there's a shift in maximum pressure, and this can be attributed to surface tension forces that are no longer able to restore the droplet back to its equilibrium shape after it's being perturbed. So therefore, what we conclude is that the analytical derivation, right, or analysis is not valid at very high CA numbers. And we can also see this on the right-hand side, where at a capillary number of 0.05, you get about a 10% distortion in volume, and that's why you see this difference in radius of curvature here. And so we actually got the cover image of Journal of Colloid Interface Science, and also got a little bit of some sort of media on this. It's kind of funny. I thought that they had a chip on fire. It's really not the point here, but anyways, we'll take it. So so moving on. So now that we kind of talked about the contact line dynamics, let's move on to sort of the evaporation mechanisms. So evaporation, right, essentially, there's several different resistances associated with evaporation. I'm sure many of you are aware of. But aside from the diffusion resistance, the dominant mode of evaporative heat transfer typically is the conduction resistance across the liquid body. Also, sub 100 nanometer length scale, the 𝗘𝗃𝗽𝗃 resistance and also disjointing pressure can also play a very crucial role. But in other words, you typically have, for these thin liquid films, like an absorbed region, and you have very strong intermolecular forces. All right, so you don't get a very large contribution of evaporation, at least for length scales larger than 100 nanometers. There's been a lot of great work that actually shows that actually in the absorbed film for sub 100 nanometers, you can get actually a significant percentage of evaporation. But for the micron scale, what I'm looking at today, typically absorbed film has a smaller contribution to evaporative heat transfer. And so then you have this transition region and intrinsic meniscus region, which typically contribute to a very large percentage of the total evaporative heat transfer, and therefore they have very high heat transfer coefficients typically. And then, of course, your bulk region, the least inefficient evaporation occurs in this region. And so then really the idea here is, right, then we really want to try to maximize the evaporative heat transfer by increasing the contact line region, or the solid liquid vapor interface region, right? This is where most of the evaporative heat transfer occurs. And so therefore, we want to maximize the contact line region to wetted perimeter area ratio, right? And so what has been done in the past? So if we look at some of the state of our methods, we've been looking at a lot of great work in thin film evaporation. And the idea is that we want to really reduce the length scale of the liquid film, and by reducing this length scale, you essentially are able to get the evaporation from the transition and intrinsic regions. And so that's really been the state of the art method. Our approach here is to actually look at like asymmetric droplets and to increase this contact line perimeter. And so, and the idea here is that we can increase the contact line perimeter to wetted area ratio. And this also, what we'll see, also induces higher vapor concentration gradients along these curved regions. In addition to that, one of the advantages or potential advantages of convex droplets is that we ensure that you can essentially maintain a sort of a superheated state, because we can ensure that our liquid pressure is always exceeding our saturation pressure by the capillary pressure. This may or may not be important depending on your operating temperatures of your electronic device. And so really this was the basis of sort of my early career award, where we were looking at sort of evaporation mechanisms through these hollow micropillar structures, both for single hollow micropillar structures and an array of hollow micropillar structures. There's actually different behavior. And so the idea is that with a constant pressure microfluidic system, we're able to maintain a droplet, either hemispherical or asymmetric droplets of constant size and shape. And we'll see that a little bit in the next several slides. We also wanted to, we're also currently developing some systems, some imaging systems, so we can look at how microconvection, right, behaves and asymmetric droplets compared to traditionally what we find in hemispherical droplets. Okay, so now that we looked at, we kind of looked at the surface physics for hemispherical droplets, let's briefly take a look at the surface physics for asymmetric droplets. So here I'll just kind of go through sort of, it's sort of very similar in terms of the behavior, at least some of the different stages for asymmetric droplets. So you have your wicking, right? And then you have your pivoting from a concave to convex meniscus. But, and then also your maximum, again, Laplace pressure for water occurs at the inner diameter, and for low surface tension liquids such as IPA and Novak occurs at the outer diameter. However, the critical bursting volume, right, for lower surface tension liquids are smaller, right? And also you get this sort of, the swivel-like behavior that you get, right, after the droplet sort of advances as a cap sphere along the outer edge. This swivel-like behavior or pressure recovery behavior that we see is less pronounced for asymmetric droplets. And so this is really the main takeaway, and I'll explain why in the next several slides. So that's really sort of the main sort of observations from these plots. And so the reason why you get this behavior for asymmetric droplets is we can look at sort of the Gibbs criteria, right? So the Gibbs criteria is essentially sort of provides some information on, your critical contact angle before bursting occurs, right? And in this particular case, phi for us is just 90 degrees, right? So what happens is that the critical contact angle for asymmetric droplets or hemispherical droplets actually does not change, right? They are the same. However, what happens is because you have a non-uniform buildup of liquid for asymmetric droplets, the critical contact angle reaches, or the critical contact angle reaches faster for these asymmetric droplets. And therefore, this is what is attributed to a smaller critical volume for asymmetric droplets compared to hemispherical droplets. And finally, here we see just the difference, right? These are just sort of a summary of different images, different droplet images for both circular, square, and triangular droplets of different fluids for DI water, IPA, Novak. And so the main idea here is that we can see for circular, you get the largest sort of critical volume for DI water, right? And also for circular micropillar structures. And then there's a decrease in critical volume as you decrease the surface tension of the liquid, and also as the droplet becomes more asymmetric. And we actually got the front cover of Langmuir, so we're pretty excited about that. And so finally, now that we kind of investigated the contact line dynamics of asymmetric droplets, let's move on now to the evaporation characteristics of these asymmetric droplets. So to look at some of the theory, we performed some evaporation simulations. We used the Schrödinger model here. We assumed that the equilibrium pressure was approximately equal to the saturation pressure. Essentially, we neglected the disjointing pressure. As I said before, the disjointing pressure can be very important depending on your length scale. We neglected it in these simulations. However, we thought that the most important evaporation characteristics was the perimeter and liquid vapor interfacial area. So we kept these constant for these simulations, and we wanted to compare droplets atop circular, square, and triangular micropillar structures. We wanted to compare sort of the evaporation characteristics of these droplets on these different micropillar structures or different shapes. And so what we see here is, we typically see what we normally see in evaporation, right? We see that near the contact line, right? As we approach the contact line, we get higher evaporation rates, right? Near the contact line region. However, for asymmetric droplets, not only do you get larger evaporation rates as you approach the contact line region, you also get larger evaporation rates at higher azimuthal angles. In other words, at angles near the corner regions of the asymmetric droplets, right? And we'll explain why in the next several slides. And then, so therefore, these at these higher azimuthal angles, this leads to higher interfacial temperatures, which essentially leads to higher heat transfer coefficients. And so we're able to see that at, for example, a heat flux of 500 watts per square centimeter, we're able to show 15% and 20% increase in heat transfer coefficient compared to a droplet confined on a circular micropillar structure. And for 1,000 watts per square centimeter, we're able to see a slightly lower increase in heat transfer performance, and we attribute this to the conduction resistance playing a larger role at larger heat fluxes. And so finally, we can see that in these simulations, right, that at higher azimuthal angles, this is attributed to, we can see that there's smaller contact angles at these higher azimuthal angles, which lead to larger local evaporation rates. And we also see that this also leads to larger interfacial temperatures at higher azimuthal angles, which lead to overall higher heat transfer performance for asymmetric droplets. And this particular work that we did is we also looked at the evaporation characteristics of asymmetric droplets for droplets without any heat load. So in other words, can we see some type of improvement in asymmetric droplets, evaporation from asymmetric droplets, even without any heat load? And the answer is yes. So what we see here is that not only do you get sort of small thermal resistances associated with the smaller contact angle from asymmetric droplets at their corner regions, but you also, due to the higher curvatures in these corner regions, for example, of say triangular micropillar droplets atop triangular micropillar structures, these higher curvatures also lead to faster changes in concentration, right? ISO concentration lines, which essentially means smaller diffusion resistances or higher concentration gradients and higher evaporation rates. And so therefore, we're able to see a 5% and 20% improvement in evaporation rate compared to droplets, hemispherical droplets, typically on circular micropillar structures. Okay, so now that we did kind of like all those simulations, we also wanted to actually perform evaporation heat transfer experiments from microdroplets atop these micropillar structures. And so this is kind of, you can sort of look at our papers and look at the details of our experiments, but we essentially use a constant pressure microfluidic system, and we use just typical CCD camera for visualization. and we fed, the liquid into these microdroplets and looked at the sort of droplets from a side view and top view in order to ensure that, when we were measuring these different sort of evaporation rates, that we ensured that the liquid vapor interfacial area and the contact line region remained the same, so we can make a fair comparison of the different droplet shapes. We use platinum resistance temperature sensors and heaters. We microfabricated these structures. They were fabricated on the backside of the micropillars in order to maintain a constant temperature. As I said, as I mentioned just earlier, we ensured that the contact line perimeter for the circular, square, and triangular micropillars were equal, and also the liquid vapor interfacial area of all the droplets were kept the same. We can go into the details here, but essentially what we did is we used surface evolver, and the idea is that we kept on increasing the droplet volume until we were able to get the same height to side length ratio. Once we got the same height to side length ratio, we can ensure that the liquid vapor interfacial area and remain the same for all droplets. And this is essentially the droplet profile. This was actually generated by surface evolver. As you can see, there's non-uniform sort of contact angles, right, associated with these asymmetric droplets. And even though these smaller contact angles are not necessarily good for in terms of like stabilizing low surface tension liquids, right, because you have smaller critical contact angles, but this does sort of convey why you get higher heat transfer performance for these asymmetric droplets due to these lower contact angles. And here is just a comparison of our droplet morphologies using surface evolver, which agreed well with our experimental measurements. So here, again, we see that the height to side length ratio and local contact angles was less than the difference between what we predicted from surface evolver in our experiments were less than 3%. Okay, so we finally performed evaporation experiments at different temperatures for these different droplets. And what we see here is a nonlinear increase in evaporation with increasing temperature. And we can, this is attributed to, the nonlinear increase in concentration or saturation pressure. We see that the heat transfer coefficient for droplets atop triangular micropillar structures were 8% and 45% higher than those of droplets on square micropillars at 60 degrees and 98 degrees respectively. For droplets, for triangular micropillar structures, we had an increase of 41 and 71% higher than those of droplets of, this should be actually circular micropillars, at 60 degrees and 98 degrees. And again, this nonlinear increase in evaporation rate is essentially caused by a nonlinear increase in saturation pressure. And so therefore, which causes a nonlinear decrease in diffusion resistance. And so therefore, what we see here is that as we increase the temperature, the conduction resistance plays a more significant role to the total thermal resistance. We also have been looking and investigating microconvection effects for asymmetric droplets. And what we see here is that, typically for droplets smaller than 2 millimeters, we see that there's a monotonic increase in evaporation rate as you approach the contact line region. However, if you get to droplets like larger than 4 millimeters, we see that there's this sort of shift in local thermal resistance away from the apex of the droplet, and that can be attributed to more mixing. In addition to that, for asymmetric droplets, we also see stronger convection effects at higher azimuthal angles, and we attribute this to higher capillary flow because there's higher evaporation rates in these thinner regions at higher azimuthal angles. Finally, we also wanted to look at what we call the vapor diffusion confinement effect. So typically what we see here is that sessile droplets are typically on a planar silicon substrate. And so the idea here is that what if we, for example, can suspend these micropillar structures and study different aspect ratios or different heights. And what we see here for a non-heated substrate, we could actually improve the evaporation or increase the evaporation by up to 40%. And this is due to a fast change in ISO concentration lines along the impenetrable solid micropillar structure. However, for heated micropillar structures, what happens is that you do get a enhancement in micropillar structures with higher aspect ratios. However, at very high temperatures, because the diffusion resistance is already relatively lower, the conduction resistance becomes the dominant mode. And so therefore, the maximum heat transfer or maximum evaporation rate occurs at very low aspect ratios. And so finally, so we've been looking at a lot of in terms of like single micro droplets, but ultimately we would like to develop like an actual evaporative cooling device. So then we started looking at how, for example, evaporation of these hollow micropillar structures will behave when we have an array of these micropillar structures, right? And so we started doing some optimization, and the optimization really here is that we want to like minimize this vapor diffusion confinement effect, while at the same time maximizing the heat transfer coefficient, right? So in other words, we want to be able to pack these but also reducing this sort of confinement effect. So we use particle swarm optimization, which is this sort of an algorithm that combines local search methods with global search methods. And we use a parallelogram as a unit cell in order to sort of minimize the number of parameters that we need, right? But also allows the micropillars to orient in different positions. And so here we have just L1, L2, these are the different pitches, and phi is sort of the orientation of the micropillar structures with respect to the z-axis. And so we performed these array optimization studies, and we got some optimal parameters. And we see that with a staggered optimized triangular micropillar structure, we get about a 14% enhancement in this optimized array. And this is sort of preliminary work. We're still, doing ongoing sort of evaporation experiments right now, but we actually have done some extensive work on microfabricating these array structures. And so these are just sort of different structures that you see here. We see orthogonal pattern array structures of circular micropillar structures, of orthogonal triangular micropillar structures, and staggered triangular micropillar structures. And so, we're studying the evaporation characteristics of all these different types of array patterns and shapes. And this is sort of right now the evaporation experiments we're doing, some of the parameters that we're associating with these evaporation experiments. And so far we've gotten pretty good agreement with our simulations and evaporation experiments. So we're very encouraged with that. And I thought that I'll just show you a video of some of our preliminary work here. And so this is an array of orthogonal triangular micropillar structures. Yeah, so here you can see that we sort of maintain the droplet, using this constant pressure microfluidic system. And so finally, we also just wanted to map out a regime plot, and what we believe our technology can do is we can, for example, remove, once we scale down in the sub 10 micron length scale, we believe that we will be able to dissipate heat fluxes, for example, of 700 watts per square centimeter, with about 50 times smaller required flow rate compared to traditional single phase cooling methodologies. And finally, I'll just look at some of the future work. So if we look at, one of the things I talked about is in evaporation, one of the things that we want to do is sort of maximize the contact line to wetting perimeter ratio. So some of you might be asking, why not just use like a needle shape or something like that, right? Why not just use that kind of shape? So, but the other story is looking at the wetting efficiency. So if we look here, we can see that on this sort of triangular microdroplet, the droplet is not completely wetting the entire sort of solid liquid area. And so therefore what we did is, this is just sort of a preliminary results from Surface Evolver. You can see, for example, for a square shaped droplet, if you sort of map out the wetting efficiency, we can see that there's sort of like an optimal shape where as you increase the contact line perimeter area ratio, you sort of get a drop in wetting efficiency as you increase the aspect ratio to the extremes. So there is sort of this sort of optimization on like maximizing. We believe that we want to have about a wetting efficiency greater than 95% for our device. And so we're just looking at that too as well. Finally, we've been doing some, work, and finally, we would like to sort of, integrate these, evaporative cooling module and, using co-design and using, for heterogeneous integrated chips. And so we envision, integrating our hollow micropillar structures, and you sort of heterogeneous integrated chips with, and here we see, through silicon vias, and we see sort of these hollow micropillar structures that are sort of bonded here. If you have more questions, I can actually go to some of the details of how we envision this, but we actually have a current patent that's currently that has recently been filed here. And so we've been working on this as well. In addition to that, we also started a project with ONR. We've been looking at sort of developing this sort of evaporative cooling module using this structures also for wide bandgap semiconductor devices as well. So we're very excited about this work that we're starting in. So with that said, I think I'll stop here, and I really thank you very much for listening to my talk.